Okay, so our last example from last week was section 7.5, where we have two theorems that help us deal with um, problems where we know the sample size, which means we know how many we're dealing with. You can't always have an unlimited amount of data, so in the real world, sometimes we usually have a sample. So the first one I want to look at here is what happens when we know the sample size, and that is theorem 7.1. So if a distribution is already normal and we take a sample, the mean is going to be exactly the same. So that's a cool thing. So if we have a sample and we call X is our sample, and P stands for population, then the cool thing is the mean for the sample is the same thing as the mean for the population. So we don't have to do anything to change that. As far as standard deviation, though, the standard deviation does change. So if we keep reading here, the standard deviation is going to be the standard deviation for the population, but it's going to be divided by the square root of the sample size. So our standard deviation for our sample will be equal to the standard deviation for the population divided by the square root of n, where n is the sample size. So if we look down here, this is a question about fish, and these fish are being caught in a pond, and these biologists want to know, we're being told that any fish that is not at least 8 inches must be thrown back. And they know that the distribution is normally distributed, where the mean is 10.2, and the standard deviation is 1.4. So this is our population for all the fish. We're going to look at some samples. So the first sample is for one fish. So one fish actually doesn't change anything because we're going to divide by the square root of 1. So we can actually use the same model here. So we want to know what's the probability that it will be between 8 and 12. So we can go back to our friendly normal CDF function, and we're going to have 8 is the lower amount and 12 is the upper amount. And 10.2 is our mean, and our standard deviation, again, is 1.4 divided by the square root of 1, which really doesn't change anything. So we're just going to use 1.4. But we did have a sample. It was just a sample of 1. So 8, 12, 10.2, and 1.4. See if I can remember all that. Second bars. So our smallest fish is 8. The largest fish is 12. The average size of the fish is 10.2. And I believe it was 1.4. So the probability that you'll catch a fish between 8 and 12 is about an 84% chance, 0.8427. So 0.8427. So that means that 84% of the time you will catch a fish over 8 inches, less than 12 inches, right? Which means you don't have to throw it back. What's the probability that's going to be under 8 inches? So again, we're only catching one fish. The probability that that one fish will be under 8 inches, we're drawing from the population. So since we're only drawing one, our sample size is 1. We don't have to change our standard deviation. So the smallest fish is 0, doesn't exist, up to 8. And our mean is 10.2. And again, we're going to use the same standard deviation, 1.4, divided by the square root of 1, which basically doesn't change anything. So we're going to go back to our calculator. And I know I'm not drawing pictures on this example, but second bars. I think you can draw the picture to this one. So 0 up to 8. And our mean, the nice thing is you can look up above, we have the same standard deviation in the previous example in case you forget it. It's on your calculator. And so that probability of that happening is 0.058. So that tells us that only about 6% of the time, 5.8%, So that means that 6 out of 100 fish are undersized. It means it's pretty good fishing, right? Most of the time you're going to be able to catch a fish that you can keep if you're into that. And then the last one, this is where it's going to change a little bit. What if somebody went out there and caught 5 fish? What's the probability that one fish out of 5 is between 8 and 12? So if so not one fish, that the average, right? So suppose we caught 5 fish and we figured out their average. What is the probability that out of those 5, I add them all together, that they're going to be between 8 to 12 inches long when the average is 10.2? So we want to know, what's this probability? And again, it's going to change. So my new standard deviation for my sample size of 5 is going to be equal to 1.4 divided by the square root of 5. So let's do that on the calculator. 1.4 divided by, my square root function is here, the x squared. And I get a new standard deviation as 0.6261. So it actually becomes smaller, 0.6261, which means there's less variation, right? Less fish, less variation. Well, actually, that's not true. Less fish, more variation in the sense that there could be bigger differences between them, but when we're dividing by the sample size, it actually has the effect of this reducing our standard deviation. So let's look at, because normally the bigger the sample size, the smaller our standard deviation will be, the less variation. But in this case, since we're using n in the denominator, it's actually going to have the effect of decreasing our standard deviation. And I'll come back to that later and talk about that. So, so we just need to look at, how does this going to affect our answer? Normal, CDF. And again, we want to know, is it between 8 and 12? We already did that in the first example, and you saw it was 84% of them were between 8 and 12 inches. But out of 5 fish, what is the chances that the average would be between 8 and 12 inches? So again, 10.2, but only 0.6261. What's going to happen to our probability? So again, we're going to do second bars. We're going to go from 8 to 12, 10.2. And then I have my answer right above there, 0.6261. Never clear your calculator because your answers are all stored up above. So that has a 99% chance. So by reducing that standard deviation, we actually increased our probability, 0.9977. So I wish I were there to talk to you about this in person. But as we reduce our standard deviation, we increase the probability of it happening, which means there's less chance of variation, which means there's more chance of it actually happening. So what is the probability in both part A and part C? And we can sketch both distributions. If you wanted to look at it in part A, this is part A, and let's say this is part C. So 10.2 is in the middle, but the standard deviation is 1.4. So if I add 1.4, I'm going to get, this is going to be 11.6. And if I add 1.4 again, this is going to be 13, right? And if I subtract 1.4, this is going to be I'm losing my focus right now. So 10.2 minus 1.4. I don't know why I could not subtract in my head 8.8. Always better to use a calculator when you can't do it in your head. 8.8 and subtract 1.4 again, this is going to be 7.4. So if you look, we wanted to go from 8 to 12, and that probability ended up being 84%, right? But in this example, if I have 10.2 in the middle and I start adding only 0.6261, well, adding 0.6261 is going to get me all the way out to here and all the way out to here before I get to 12 and 8. So since I'm adding less, it takes me longer to get to 12, and it takes me longer to get to 8, which has the effect of having a higher probability of it falling within that range. So that's why this one added up to 99.7. Because the distance we're moving is smaller, it takes us longer to get to the point we're looking for on both sides, right? So that's why that one came out to look like that. And you got to see me not able to subtract while I'm recording. That's what happens. Sometimes the brain doesn't work under pressure. The last thing I want to look at is the central limit theorem, which is actually really nice. If we don't know our sample size, if we don't know it's normally distributed, we can use a normal distribution as long as the sample size, it looks relatively normal, and the sample size is at least 30. So this is just a rule that's been developed because if the sample size is at least 30 and the samples have about the same size, the distribution of sample means has an approximately normal distribution no matter what the distribution of the original data looks like, as long as the sample size is large enough, usually at least 30, and your samples are roughly the same size. So we're going to look at an example about bacteria. Bacteria occurs in all raw milk. The health department has found that the milk has a distribution that is mound-shaped and symmetric. So that tells us that's our first requirement. Should like that. And the mean of the distribution is 2,500. And we know the standard deviation is 300. And we're also told that n is 42. That's our sample size. But we don't see the word normal in there anywhere. So we are allowed to use a normal distribution because since the distribution is symmetric and n is greater than 30, we can use a normal distribution. And this is really where statistics becomes practical, because someone's not always just going to walk up to you and go, this is normally distributed. You have to be able to say, well, when can I use a normal distribution? Well, I just have to gather enough data, right? And not all data is going to be mound-shaped. Like if you gathered the age of everybody in class, your ages are all going to line up pretty much in the same place, right? Because everybody in the class is almost the same age. They're all going to be about 17 or 18. But if we looked at like weight or height, you'd see a normal distribution, right? Or grades. It's not all data is mound-shaped, but in this case, the amount of bacteria that you'd see in in this sample is going to be above or below 2,500. So this is what we're looking at. So we can use a normal distribution where the mean is 2,500 and the standard deviation is 300. And that'd be my middle, 2,500. So what do they want to know? They didn't ask us any questions about that. Well, I think I forgot to give you the rest of this question. So I'm just going to hold off on that. The only thing that's important is now we have our model, right? We can do anything we want with it. I could say, what's the probability that a sample would have above or below a certain amount? If the sample was 42, we'd have to look at our new sample standard deviation is going to be equal to 300 divided by the square root of 42. So I am going to get rid of this. Since we're using a normal distribution, we're going to have to change it to 300 divided by the square root of 42. So our new standard deviation is going to be 46.3. So I think that's all I'm going to do on this. Maybe in the next video, I'll ask you a question about this bacteria question. So I think we just needed to see what model we could use. We could use a model where the mean is 2,500 and the standard deviation is 46.3. Okay, so that is the end of the work for last week. And this week, I'm going to be looking at only section 7.6, which is on the binomial model. And the binomial model basically says, if you have a normal distribution, the middle, the average, is going to be P, and P equals the probability of success. And Q equals the probability of failure. So if it's what we call binomial, there's only two outcomes. And, you know, one of the easiest binomials to look at would be heads or tails. So if you had heads or tails, then probability of a head would be 0.5 and the probability of a tails would be 0.5, right? And so that would be right here in the middle. And there's also, anything can be expressed as binomials as long as there's two outcomes. If you are an 80% free throw shooter, the probability of hitting your free throw is 80%, your probability of missing is 20%, or vice versa. So I will present those examples that I gave you later on in the week.